Alright, so we have calculus here, and we will be focused on first principles for the starters. Now this should be able to introduce us into the basics of calculus, what we mean by calculus as in differentiation, what does it have to do with imaginary values and limits. Alright, so first of all I'm just going to introduce something like a simple graph. Alright, so let's say I have a curve here. Now this curve, looking at it, of course it will be having points 1, 2 and perhaps 3 of a point, and I'm just going to say that this could be having an equation of x squared plus 5x plus 10. Alright, now this suggests that my roots are actually out of x plus 3 multiplied by x. So I just need it to be positive as it is in that side, so I'm going to say minus here and a plus here, so it's a minus here, minus 3 and x minus okay, this is minus 5 and 2, sorry for that, so this should be 7. Right, so that means I have x equal to 5 or x equal to 2. Those are my x-intercepts, right? So that's pretty much the graph we have, and of course you can try to look for a turning point and so forth. That's not really the focus at the moment, right? Now this means this function, let's call it f of x, right, is going to have its points relatively to what we just made up right now, or relatively to this equation. This is f0 equal to 5 or f0 equal to negative 2. Now notice this notation. It's the very important notation right here. Let's say I was to look for another point on the same graph, right? And looking for another point on the same graph, let's say you're looking for f of 2. Right, f of 2 will be equal to substitution of 2 wherever there is x. So that means I'm looking for y as a function of 2, or I'm looking for y in terms of 2 of x being equal to 2. So wherever there is x, I'm going to put a 2, right? So that's just what I'm going to do right now. I'm going to have 2 squared. I'm going to have 2 squared minus 7 by 2 plus 10. And that means I'm going to have a 4 minus 14 plus 10. And that means it's 4 minus 4, which is equal to 0, is it? Oh, yes, I was having an answer of positive 2 there, which is equal to 0. How about, let's get another value, because we just got our x-intercept again. How about we use f to 4? So this means I'm going to substitute 4 where there is x, minus 7 by 4 plus 10. Right, and that is going to give me 16 minus 14 plus 10. That means I'll have 12. That means 4 is to 12 will be one of my coordinates. Let's just see, just confirmation. 16, oh, that's 28 right there. It's a mistake right there. 16 minus 28. Right, that was unreasonable to have 12. So that means I will be having just do a calculator first, so that I don't have mistakes now and then. Right, so looking at it, I can say 16 minus 28 plus 10, right, is equal to what? That's -2. Right. So that means just based on this notation, the coordinates that I have are 2 is to 0 and 4 is to -2. Right. So this notation is going to be useful in proving first principles, and this should give you the total understanding of what we mean when we're doing differentiation on each and everything. Now let's go to differentiation then. So having this graph that we have, we know that we work with points. That's one, which is simple. The functional points, as much as we just got them now. And then we know we work with gradient. And gradient, as you may know, stands for rate of change, or it means slope. And look at this graph right here. This graph is going to have a lot of slopes then. Means it has this part, just this part, just this part. As at any point you are able to get a new slope rather than when you have a straight line. A straight line is going to be having the same slope the whole time. So a curve suggests you're going to have different slopes. However, these slopes can be made per point or can be made averagely. I'm going to talk about average because average works with straight line as well. So say you have a straight line. Line 6 is to an 8. Equation is going to be based. Now, when you consider that you have straight line or all the gradients we've been drawing, look at them, or the tangents to the curve we've been drawing, right? They are all straight lines which are either going this way or they're going that way. So now when I come here, what am I trying to emphasize? And I'm trying to emphasize that any line that is slanted this way will always have a positive gradient, and any line slanted this way will always have a negative gradient. However, this issue may look not important at the moment and is actually not that important, and I'm going to teach at them for now. But there are questions that are going to come analyzing of graphs or analyzing of curves, and we're going to say when we have gradient positive, we're going to need when are those moments when we have gradient positive. When are we going to need those moments when we have gradient negative out of the graph? Now, if you look at this, this means this whole side suggesting positive gradient to me, because all the tangents will be slanted this way, right? And this whole side is going to right. So let's take it on then to our first principles differentiation. So there we go. Right. So differentiation has to do with gradient per unit point. Remember, we said we have a curve, and the curve is going to have different gradients per point. Now let's define what we mean by average gradient. First of all, average gradient is gradient per unit point. Oh no, I would have lied if I said per unit point. It's a gradient per 2 points or more. Now what do we mean by average gradient? Average gradient means out of the curve you would use 2 points. Just put a simple curve here. And I have 2 points A, I have B, I have perhaps a C here. Any gradient I have between M, A and B, or any gradient, let's say M, B and C, all of these will be considered average gradient. That's what we mean. Now let's go back to other definitions. Next definition is when I have what I call tangential gradient, or a gradient per unit point, or that is what I may call an instantaneous gradient. Now notice I'm using a word like instantaneous because with calculus we actually come out also with physics equations. Most were derived using calculus. So instantaneous gradient, now that's the gradient per unit point. So notice when you have a curve, you can get a gradient at A, you can get a gradient at B, you can get a gradient at C. Now this will be gradient of all the tangents touching the points right there. Right, going to talk about tangents and what we mean. So these are gradients that are just not average, but they're instantaneous, right? Gradients. Now any line that will be touching A will be called a tangent, touching B, touching C. What's a tangent? Tangent is a line that touches an arc at one point. Not at 2, not at 3, at 1 point. So that means any point may be taken as a line within a curve. Now, what we mean, we're trying to say any point has a potential to yield into a line, and that line is the tangent of the curve at that point. Now, the formula that can be used for average gradient is m, the well-known one. M is equal to y1 minus y2 divided by x1 minus x2. Notice when I did my example before, I had y2 minus y1. So long as you have everything on one side and everything, you shouldn't worry. I get most people asking on this one. And for instantaneous gradient, that's when we are going to do what we call first derivative, and that means it's going to give you gradient at point x. Notice how it looks. So if I wanted gradient at point A, I'm going to substitute the x of A into my first derivative formula, and that will give me the gradient at point A. Now we are now going to talk on this. Right. So the tangent will always end up with a formula of mx plus c. Y is equal to mx plus c, because it's a straight line, so it's always going to end up with this formula, wherein the m is coming from there, and that's, you'll be substituting it into that. Right. So these are the three things that we're going to be most focused on in the topic of calculus before we meet optimization. Right. So now let's talk about how do we make the first derivative formula. Right. First of all, we want a gradient at one point, but we cannot make a gradient at one point that's simple. Why? Because one point cannot substitute into this. In this formula, you notice it gives a gradient which is coming from that. Right? So in that manner, that means we need something that makes this formula look more like that. That means we're going to have some imaginary values to use that will make it possible. Consider this. I have a point, and I'm just going to take it out of our curve. Right? So let's just draw a curve like this. Right. I don't know it here. I want it to cut so that we use the same one we drew last time. Right. And this curve has a point, and I'm going to give it point C. So we want to focus on point C, and we don't care what point C is, right? But what we care about is point C has a value which is, now allow me to zoom into this, just want to work with it more. Just got too big. Just hold on for a moment. Just for that, let's do this. Right, and I'm just going to zoom it. Right, let's look at point C. So point C, right, is here, and I'm gonna put a dotted line, which we had to put though. See, now it has taken my dotted line will be going here, meaning point C has Just gonna say C is due to axis to Y. C is due to axis to Y. Now, if I need a gradient at point C, then it will be equal to x of C y of C and x of C minus something. Can I put a 0 here? If I put a 0, I am suggesting average gradient because I've just used a point. And this means I am saying the graph is actually passing through 0 to 0. And that means I've made up an average gradient. Now look at this. That would be so fake. The answer might actually not, or it would be possible to come out here, but then that would be an answer that has no relationship with the graph whatsoever, because the point would be here. The average gradient would be like this now, and this average gradient is not part of the graph. We're going to remove the curve. I'm going to focus on C, and mind you, C is coming from, you're going to make another point that is coming from this same formula. Now, let's say you just made another point and the point is here, right? Now, let's call C according to the equation. C will be x is to f of x. Notice how you get your y, if you remember carefully. How did you get your y the whole time? You said f of 2 is equal to 0, if I'm not mistaken. Or was it negative 2? It was 2. Now that means, do you notice this is the whole y and this is the whole x? Sorry, the 2 is the x. So this means the formula, as much as we say the formula is x is to f of x, I am saying 2 is to the result of f of x using 2, which is 0. That's what we're trying to make. Please take caution on these formulas, because these are the most important things that are leading us to where we're going. And this is where most of us lose it, really. Now, let's take that into consideration then. So that means this is the formula. But now, we have this point here. Let's just put this. Just put this. This is using x. To meet C, you have x. And here you have f of x. Because remember, y is also known as f of x. I keep on emphasizing on this. Now, what about our imaginary point? We want to make it in terms of x and perhaps f of x. Let's go on then. This is right here. Could be anywhere, by the way. And I could choose to join them here, but I want to join them. My focus is in between here to here. Right. I made an imaginary point, and what is this imaginary point gonna have? I'm gonna call this distance h, according to our textbook. If I call this distance h, from x you went a walk of h to a new point. Definitely the new x will be called x plus h. So I'm going to say this point has point x plus h is to f of x plus h. Now if you don't understand these notations that we're using, then you need to check out videos on functions and we can work it out. Now that means we have now 2 points, but we're left with one thing to do. H is an imaginary value. We walked a distance that does not exist. That means we might as well walk towards infinity. So, but we are going to limit this h and say as h approaches 0. This means we are trying to say that there was no distance at all. We didn't really move. It was just an imaginary distance for the sake of getting what we wanted. Please understand that part. We moved in a distance that is imaginary, therefore we need to cancel that distance in our equation after getting what we're looking for. We're using an imaginary moment to get something and then we cancel it out. Now, good, that is cleared up. I'm going to go back into my full board, or do I need to? Yeah, I think, let's see. I think I need to. Let me just lower my brightness. Now, what I'm going to do, say therefore my gradient, but this gradient I'm not going to call it m, I'm now going to call it f derivative, and I'm going to say it's equal to, let's write the gradient formula on top, it's equal to y2 minus y1 divided by, how about the new formula? I have 2 points, I'm going to copy them out. First is I have the imaginary point which has a limit of h. The imaginary point is f of its x plus h with relationship to f of x plus h. That was our imaginary point that we just got, and so that's point 2. I call it point 2, and point 1 is x is to f of x. So let's put it into our formula. This is my y, my y. So my y2 is f of x plus h minus f of x. So far as it stands for y, it also stands for the formula. And then I have x plus h minus x. Right? Keep on checking from that side. And that means I'm going to end up with f of x plus h, right, minus f of x divided by this x cancels this x, and you have an h. This is where we should remember our limit, because if we don't remember our limit of approaching 0, you cannot substitute 0 while you are solving this. You end up with an undefined answer. Any value divided by 0 is undefined, and hence the limit applies h is to 0, meaning first principle suggests you must solve this up to a point where h is cancelled out, and that's when you end up with your answer. Alright, so that's what we have, and notice here's the first principle equation right there. made up really nice. That's what you see, there it is. So we just made it up. We just made it possible. Now should we go on and solve it? Yes. That means now we can derive a formula that gives us what? That gives us a gradient per unit point. That can give us a gradient for point C. Because point C, if you notice, it's a variable point. It's not an. We didn't say that this is 2 is to something. We just called it C, meaning that it could be any point. It could be the point up there. It could be just so long as it's on the curve. And our new point also is a variable point, which is imaginary. It's only dependent on the distance h between the x values, and it ends up giving us that formula. Now stay with me. Let's sort out this. Right. Now you would remember that we are coming from an equation of f of x is equal to x squared minus 7x plus 10. So let's solve our gradient equation. It will be equal to f of x plus h minus f of x divided by h, whereas the limit is that h is approaching 0. I'm going to put it in wherever there is x. I'm going to put x plus h squared minus 7 x plus h plus 10 minus, just going to put everything that you were having, and we will fit. Yes, we will fit. Yes, we will. So there was a line that we had before we zoomed, so it's fine. We will fit. Minus an x squared minus 7x plus 10. Here's one mistake we make. There's a subtraction sign and subtracting everything coming with f of x. Now some of us put minus and we don't put brackets, and that makes us have the negative not affecting everyone inside. Right, I like doing this. I always put these arrows to show how my negative, to remind my mind how my negative, because everyone in this bracket is being subtracted. Now all of this is divided by an h, wherein the limit is that the h is approaching 0, meaning the h is a 0, the h is nothing, so we're going to say it's equal to. Now this gives us an x squared plus 2xh plus h squared. If you don't remember this, we just did x plus h multiplied by x plus h, and this times this gives you x squared. This times this gives you plus xh. This times this will give you plus xh, and this multiplied by this will give you h squared, which will give you x squared plus 2xh plus h squared as we have it. Now my equation is going to be pretty much very long, so what I'm going to use is this notation. 10 minus 24 is the same as 10 minus 24. This is what I'm going to do, right? So don't be confused when I do that. And then this will be minus 7x. Now the 7 is applying to the whole bracket, right? Minus 7h, and I have plus 10. Now this equation, I'm going to take it down like the 24. I'm going to say minus, and you're allowed to do what I'm doing, minus. Now I put the x squared close, right? Now negative times negative 7 will give you positive, right? Not just this arrow, that is the one I'm emphasizing on. So it will be positive 7, so I'll have plus 7x. Now notice I'm putting them likely nicely. And negative times 10 positive will give you what? Negative 10, so minus 10. All of this is divided by h, and the limit is h is approaching 0. And then let's see what that makes us. This cancels that, and this cancels that, and this cancels that. What are you left with? You're left with 2x h plus h squared minus 7h divided by an h. The limit h is still approaching 0. Alright, interesting. Let's continue with it then. And our space is about finished. Now that means I can factorize h. Notice h is common. H is common. I'm gonna factorize h out, and I have 2x plus h minus 7 all together divided by an h, and the limit is still that h is approaching 0. Now because you have factored it out, remember common factor x multiplied by y plus 2 divided by x. X will cancel x. So that's what I would do here. H will cancel h. Now because I've let go of h, now because I won't get undefined, because I don't have the denominator of 0, now and only now I am going to let loose of the h. I am going to let loose of the fact that this was all imaginary the whole time. So I'm going to say now, only now, this will be 2x plus 0 of an h minus 7. So I don't need to write limit anymore, and that's when I have an answer of 2x minus 7. And I've just derived a formula for myself, which is f derivative. Now this means, remember we say that this means gradient. It came from gradient. It means gradient. So that means this is the formula to get a gradient at any point. Formula to get a gradient at any point, right, in the graph or the function x squared minus 7, f of x equal to x squared minus 7x plus 10. Right, so that means if we were to ask you, right, let's just compute a value. Right, you have a curve, it's fine, I'm gonna take time there. You have, so scale that, lose space. Now you have a curve, right, and the curve was f of x equal to x squared minus 7x plus 10. Now we say get gradient of tangent at point 3 is 2. Now I need to hesitate. I don't know what is the y value. Do I care? I don't care about the y value. So I'm going to say 3 is to d. Now that's pretty much how an examiner can give the question. Do you need the t? You don't, because you've just made up a formula wherein you can get the gradient in terms of the x value, not the y value, right? So you don't need the y value of that point. Now notice we said gradient of tangent passing at that point. The tangent touches the point. So if the tangent touches the point, then the tangent has the same gradient as the point. Notice how we may ask the question. It's either I can say get the gradient for the point or get the gradient for the tangent at the point. But then both of them are the same thing because they work together. The tangent passes through that point, so that means the tangent has the same gradient as the point, or we give you the equation of the tangent, we give you the gradient of the tangent, that means that's the gradient of the point. Take note of that. So now that means I can just go and say, you know what, I know that I got a derivative formula which entails to me the gradient, so it's equal to 2x minus 7. So I'm going to say the gradient with reference to x is equal to 3 is equal to 2 multiplied by 3 minus 7, which is equal to negative 1. So that means the gradient at point 3 is 2d. I don't care about the y, is this. Right there, you're done. Right, so the next video is going to just have some equations to deal with, right? It's going to take a bit of a question paper where we're just going to be using first principles to get first derivative. Already you can tell what first derivative is used for, but we're still going to emphasize what first derivative really means or what we can use it for at the end of most of the videos, after having done also the power rule that we're going to use, a simpler way wherein we can be able to break down this thing to get the first derivative, second derivative, third derivative if we have to. So we're going to speak on what does it mean to have these answers and what can you use these answers for. Right, so stay tuned. So this is the end of our first, and just a recap. Just gonna zoom it. Some of things may not be seen, but it's okay. Just need to recap on this page. And yes, that was a pretty intensely zoomed page. Right. Okay, going back. We started here calculus, first principles, and sorry for that. And you notice how we had so you will notice how we had an equation, right? F of x is equal to x squared minus 7x plus 10. We drew our curve, we worked with our curve, we spoke about notation, function notation, how it works, how that f of x depends on x and you get the answer, meaning f of x is the y value when you would have calculated, right? You got y value 0, y value negative 2, all based on x values 2 and 4. And we went on to emphasize on the average gradient formula. We did definitions as well, and we spoke about how do you know when a gradient is negative and when a gradient is positive, right? Now let's go to the next. Now the next has a lot of information really. We started with definitions. Average gradient per 2 points or more, but normally you use 2 points anyway because the formula has 2 points, and that means you'll be getting average gradient out of anything so long as you have 2 points. And take note that when you have an average gradient of a straight line, it's actually the gradient, it's not really average anymore, because on a straight line, yeah, anywhere you can even get a gradient per unit point, to just be a constant for any point. So after that you have instantaneous gradients, and we're speaking of the gradient per unit point now, and that is when you will need the derivative formula. And you have the tangent, which we did not focus on that much, but you can tell we said the tangent is a line that touches an arc at one point and is touching whatever curve you have at one point, and we may ask for the gradient of the tangent instead of the point, but you must find what point is that tangent working with, because that point is the one that you may now go to get its derivative um, value or gradient. So there we have it. So f is equal to x squared minus 7x plus 10, still using the same graph, and we might use this graph over and over and over again. Makes things simpler. Now there comes our notation. We taught each other notation and we used it pretty well. We suggested we made a new point, and this new point is depending on an imaginary distance that makes a new x, and that x will be called x plus h instead of x. Nice. So that means the y will also be dependent on x plus h instead of x only. But the first c is dependent on the normal graph where x is to f of x. And that gives us the gradient equation right here, where we said the y2 is f of x plus h. Nice, we put it in. The y1 is f of x, we put it in. And then the x2 is x plus h, put it in. And x subtraction, you get the first principles formula. So we won't be deriving anymore, we'll just be using we won't be deriving the formula anymore, just be getting we'll just be doing the formula really for the examples that we're going to have. And take note, this is not examined. You doing deriving of formula is not examined. We merely do it so that you may understand the basics of calculus and where is calculus going. And there we go, and we end up with the answer wherein we have the first derivative formula derived. And if you have the first derivative formula, you know that this is what you use to get the gradient at any point. You just have to know the x of that point. That's what we did right there when we wanted what? Gradient of tangent at point 3 is to d. Do we care about the y? No. But we care about the x, which is 3, because our formula depends on the x of the point. And we did solve for the gradient, and we got -1. That's the gradient for the point, and that's also the gradient for the tangent passing through the point. And that's it.